Welcome to the second video lesson for Chapter 3 of the Foundations of Scalable Systems. Software systems on the Internet communicate using the Internet Protocol Suite, the Iep Suites. The Iep Suite specifies host addressing, data transmission formats, message routing, and delivery characteristics. There are 4 abstract layers which contain related protocols that support the functionality required at that particular layer. The 4 layers are shown here on the slide. The data link layer is used for communications across a single network segment. This is implemented by the device drivers and network cards that live inside your devices. The Internet layer specifies addressing and routing protocols that make it possible for traffic to traverse the independently managed and controlled networks that comprise the Internet, as we described in Lesson 1. This is the IP layer in the Internet Protocol Suite. The transport layer comprises protocols for reliable and best effort host-to-host communication. This is where the well-known TCP, Transmission Control Protocol, and User Datagram Protocol, UDP, live. The application layer comprises several application-level protocols such as HTTP and the Secure Copy Protocol, SCP, and SSH, which I'm sure you've all used. Each of the higher level protocols builds on the features of the lower levels. And in the following section, I'm going to briefly cover IP for host discovery and message routing, and TCP and UDP that can be used for distributed applications. IP defines how hosts are assigned addresses on the Internet and how messages are transmitted between 2 hosts who know each other's addresses. Every device on the Internet has its own address. These are known as IP or Internet Protocol addresses. The location of an IP address can be found using an Internet-wide directory service known as the Domain Name Service, namely the DNS. DNS is a widely distributed hierarchical database that acts as the address book of the Internet. DNS servers are organized hierarchically. A small number of root DNS servers, which are highly replicated globally, are the starting point for resolving an IP address. When an internet browser tries to find a website, a network host known as the local DNS server, which is managed by your employer or your ISP, will contact a root DNS server with the requested host name. The root server replies with a referral to a so-called authoritative DNS server that manages name resolution for, in our banking example shown on the slide here, .com addresses. There is an authoritative name server for each top-level internet domain, such as .com, .org, .net, etc. Next, the local DNS server will query the .com DNS server, which will reply with the address of the DNS server that knows all about the IP addresses managed by, in this example, igbank.com. The DNS is queried and it returns the actual IP address that we need to communicate with in our application. The overall scheme is basically illustrated on this slide here. Armed with a destination IP address, a host can start sending data across the network as a series of IP data packets. IP delivers data from source to destination host based on the IP addresses in the packet headers. IP defines a packet structure that contains the data to be delivered along with the header data, including source and destination IP addresses. Data sent by an application is broken up into a series of packets which are independently transmitted across the network. IP is known as a best effort delivery protocol. This means it does not attempt to compensate for the various error conditions that can occur during packet transmission. Possible transmission errors include data corruption, packet loss, and duplication. In addition, every packet is routed across the Internet from source to destination independently. Treating every packet independently is known as packet switching in the network. This allows the network to dynamically respond to conditions such as network link failure and congestion, and hence is a defining characteristic of the Internet. This does mean, however, that different packets may be delivered to the same destination via different network paths, resulting in out-of-order delivery to the receiver. If we had to write our applications with unreliable communication across the Internet, this would probably be the state of most of us at the end of every day. However, if 2 hosts require reliable data transmission, they need to add additional features to make this occur. This is where the next layer in the IP protocol suite, the transport layer, enters the scene. Distributed applications can use TCP or UDP. Implementations are widely available in mainstream programming languages such as Java, Python, C++, in fact, name your own language. The complexity of these protocols is typically hidden from our applications, which utilize application-level protocols such as HTTP and WebSockets. TCP is known as a connection-oriented protocol. Before any messages are exchanged between applications, TCP uses a three-step handshake to establish a two-way connection between the client and the server application, as you can see on the slide here. Once a connection is established, a client sends a sequence of requests to the server as a data stream of individual network packets with a maximum size of 64K. Each packet contains a source and destination address, which is used by the underlying IP protocol to route the messages across the network. Packets also contain sequence numbers so the receiver can reassemble them into the correct order. TCP is also a reliable protocol. It uses a cumulative acknowledgement mechanism, whereby a receiver will periodically send an acknowledgement packet that contains the highest sequence number of the packets received without gaps in the packet stream. This implicitly acknowledges all the packets sent with a lower sequence number, meaning all of these have been successfully received. If a sender doesn't receive an acknowledgement within a timeout period, it resends a packet. TCP has many other features such as checksums to protect packet integrity and dynamic flow control to ensure a sender doesn't overwhelm a slow receiver by sending too much data too quickly. Along with connection establishment and acknowledgement, this makes TCP a relatively heavyweight protocol which trades off reliability over efficiency. This is where UDP enters the scene. UDP is a simple connectionless protocol which exposes the user's program to any unreliability of the underlying network. This means there's no guarantee that delivery will occur in the prescribed order, or in fact that it will happen at all. Messages can be lost by the network. It can be thought of as a thin layer on top of the underlying IP protocol and deliberately trades off raw performance over reliability. This, however, is highly appropriate for many modern applications where the odd lost packet has very little effect. Think streaming movies, video conferencing, and gaming, where one lost packet is unlikely to be perceptible by our users. This slide depicts some of the major differences between TCP and UDP. TCP incorporates a connection establishment phase using this three-packet handshake and piggybacks acknowledgements of packets so that packet loss can be handled by the protocol. There's also a TCP connection close phase involving a four-way handshake that's not shown on this diagram. UDP dispenses with connection establishment, teardown, acknowledgement, and retries. Therefore, applications using UDP need to be tolerant of packet loss and client or server failure, and of course, behave accordingly. That covers the basics of communication software over the internet, and it's the core knowledge that you need to know to build distributed applications. In the next lesson, I'm going to start talking about remote method invocation mechanisms, which essentially build a layer of abstraction which makes writing distributed applications simpler across networks. Thanks for watching.